Series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The second lecture, Case Space and Imaging, is broken down into 4 parts, and Lecture-02C covers the MRI Signal Equation and Case Space. The learning objectives for this lecture include being able to appreciate the importance of Faraday's law of induction to MRI, explain how a point in case space relates to a pattern in the acquired image, understand the importance of the MRI signal equation, appreciate that gradients move us through case space, and describe how to calculate scan time. Let's begin by talking about signal reception. MRI is a classic excitation reception paradigm, wherein on-resonance RF energy perturbs the bulk magnetization, and this generates transverse magnetization. The transverse magnetization can be detected by a nearby coil, and a voltage signal is recorded. The transverse magnetization induces a voltage in this nearby coil, and this is according to Faraday's law of induction. And the whole trick here is how do we encode spatial information and, in fact, image contrast into what we call the echo, or the recorded signal. So let's begin by describing the MRI signal equation, and then we'll later develop the mathematics as to where the MRI signal equation comes from. So think about an underlying object, in this case a transverse picture of the head. And we use RF pulses to generate transverse magnetization with contrast. And this can be T1 weighted, T2 weighted, or other forms of image contrast, perfusion and diffusion as examples. So having prepared the magnetization to generate some state of transverse magnetization as a function of space at a particular time 0, we then apply gradients to encode the spatial information. And these gradients take on the following mathematical form, which will become a little bit more apparent as this lecture develops. It's Faraday's law of induction that allows us to integrate all of this information into a single recorded signal. And that signal, as we will learn, becomes a signal that depends on, is a function of case space or points in case space. And an individual point in case space is shown here. This is the so-called raw data that's collected by the scanner. And by a series of manipulations of the spatial frequency encoding term here, we can update the k vector, the wave vector. We will acquire a different point in case space and thereby raster through all the points in case space that we need to acquire, wherein each point in case space tells us about the presence or absence of some underlying spatial frequency weighting pattern. Now, perhaps somewhat surprisingly, this case-space data that we acquire is actually fundamentally the Fourier transform of the underlying object itself. And so when we take the Fourier transform of the acquired data, we then obtain an image of the object that we had under investigation. Quite a remarkable series of events. So let's think more about what is case space. And there's different ways we can approach this. Case space, from one perspective, is simply the raw data collected by the scanner. It represents a point in case space, or rather a point in case space tells us about the presence or absence of a particular spatial frequency or pattern in the underlying object, which we are able to generate and display in the underlying image. Each echo measures many of the spatial frequencies that comprise the object. And if you have a background in MR already, you'll know that we acquire echoes after each excitation in general. Case space has physical units, although it's often left not carefully described or discussed. Those units are in units of inverse distance or inverse length, and typically in units of inverse centimeters or inverse millimeters. And this represents a so-called spatial frequency. And if that term seems a little bit unusual, it might be easier to think of this in the context of audio signals, which have units of hertz or inverse time. And these case space units are spatial frequencies or inverse space. Gradients help extract the frequency information, and they also help move us around case space. These are concepts that will develop as the lecture proceeds. And one last thing about one last answer to what is case space. A line of case space is filled by an echo. And so we have one line of case space here. This would be the data that would be acquired during a single echo. That might be a gradient echo. That might be a spin echo. And so it consequently takes a fair bit of time to acquire all of the echoes that we would need to fill, say, all of 2D K-space, whereafter we could take a 2D Fourier transform to finally obtain an image of the underlying object. We can answer the question, what is K-space another way? Here we are identifying the image information associated with the middle or central point of K-space, and we see that it would represent DC, or very flat image information. If we move out to the right here, we approach higher and yet higher spatial frequency information, and this tells us about the presence or absence of these particular patterns in the underlying object. If we move along the diagonal, then of course we see some underlying intermediate and higher spatial frequency banding patterns, and K-space tells us again about the relative presence or absence of these kinds of banding patterns. And just as other examples, we can have horizontal and vertical banding patterns or diagonal patterns with other angles. And each point in K-space is simply telling us about the presence or absence of a particular spatial frequency in the object that we're trying to image. So here's another way of looking at the same kind of information. Here we're taking the 2D Fourier transform of this K-space to produce an image that's shown on the right-hand side. And with every update of the movie on the right-hand side, this single point in K-space is being heavily exaggerated. And so those particular spatial frequencies are overly represented or exaggerated in the image on the right-hand side. And you can see how that produces a very distinct banding pattern that's changing in spatial frequency, the sort of fineness of this pattern, and also its orientation depending on where this particular point in K-space is. Now, of course, you'll also notice this is fundamentally a dynamic image. This is a cardiac magnetic resonance image. And the K-space data on the right-hand side is also subtly changing from time frame to time frame. And so it's really a gentle mixture and subtle changes in these spatial frequency patterns that can actually give us pretty dramatic changes in the overall image quality or image appearance. So again, just an example of this, of how the K-space points relate to image formation on the right-hand side. We can also isolate just the middle part of K-space and take a 2D Fourier transform. And you'll see on the right-hand side that what we get is a very blurry image. We still see some of the same contrast that we saw in the previous image, but otherwise it's quite blurry. And if we look at just a Fourier transform of the periphery of K-space or the edges of K-space and take a 2D Fourier transform, then we get this very unusual looking image, which essentially lacks all contrast but shows quite a bit of edge information. And so fundamentally, we need the combination of both contrast and edges to produce diagnostically useful magnetic resonance images. And so we have to cover enough K-space to provide us with both the contrast and spatial frequency or spatial resolution that we need for a particular task. Here's just another example of K-space and resolution. So here the lines, the gray lines dashed in solid lines, are representing lines of K-space. And if we take the 2D Fourier transform of this acquired data, we can see that we have imaged this phantom object, resolution phantom. And we can eliminate the edges of K-space. Perhaps this is a faster acquisition where we only acquired some of these lines of K-space. And if we take the Fourier transform of that data, then we see that we've lost some resolution information. So again, the edges of K-space represent, the periphery of K-space represents edges in our objects, which is associated, of course, with image resolution. Interestingly, and we won't develop it further in this specific lecture, but the field of view that we actually acquire is related to 1 over delta k, which is the step size between k lines or k points in our acquired image. And so if we take, again, this as our sort of baseline K-space data, take a 2D Fourier transform, and this is the object that we would recover, an image of the object that we would recover. If, however, we take out, say, the odd lines of K-space and perform a 2D Fourier transform, then we get this image on the right-hand side here, which demonstrates what we call aliasing or field of view wrap. And so we can see that uniformly skipping lines in K-space causes this aliasing artifact, a well-known artifact in MR. And while it may not be obvious that taking out lines in this manner would result in an object of this kind, this is a well-known artifact in MR and concepts that we'll talk about later as the course develops. So where does the MRI signal equation actually come from? This is a rather complicated topic. I'll do my best in the next few slides just to give you some insight. The goal is not that you would sort of memorize these steps, but that you would have some appreciation for what is the origin of the MRI signal equation. And so we remember again that RF pulses can change the state of our magnetization and allow us to generate transverse magnetization that will carry with it image information about image contrast and can be encoded for spatial information as well. That will inherently allow us to induce a voltage in a nearby coil according to Faraday's law of induction. And this voltage signal that we record is actually very, very high frequency. It's in the megahertz range, close to the Larmor frequency, for example. And we use sophisticated phase-sensitive detection techniques to transform this voltage signal into a different signal that we call the S of T signal. This S of T signal, after having gone through so-called phase-sensitive detection, is actually a complex signal at that point. So we're used to thinking of MR signals as being complex, and it's this process that produces the complex signal. And then I'll get into this a little bit later in the lecture, but we make a substitution here that relates what we now call the K vector to the applied gradient fields, the duration that they're applied for, and then this is adjusted for the gyromagnetic ratio of the object that we're imaging. And so this allows us to transform to S of K, which is a signal that's a function of K space now rather than a function of time. And the 2D, and what we're doing as we acquire this S of K signal is we're filling in lines of K space depending on which K points are being visited. And the K points that we're visiting depend on the gradients that are being applied. And then finally, as we've seen already, if we take a 2D Fourier transform of the acquired K space, then we recover an image of the underlying object. So the voltage equation shown here is Faraday's law of induction, which describes that the time rate of change of the magnetic flux gives rise to a voltage. Now in our case, the magnetic flux arises as a consequence of the transverse magnetization, or the bulk magnetization rather, a term which we can expand out quite a bit. So the free precession, which is the magnetization that we're detecting while the receiver is turned on. So the state of the transverse magnetization depends on some initial state after a series of, say, RF pulses. That state will, of course, decay as a function of T2 relaxation. It will be precessing at a high frequency, the Larmor frequency, and it may have a phase imparted on it by the RF field itself. Now, acting in consort with that to give rise to the voltage that we detect is the coil sensitivity. Now, the coil sensitivity refers to the sensitivity of a hardware component, the coil itself. We don't detect the time rate of change of the Z component. This is something that is a consequence of the orientation of the coil and the magnitude of magnetic fluxes, which are largely governed by the transverse magnetization. And so here we see that the B receiver field really just depends on the transverse magnetization, and it has a magnitude and overall sensitivity, and it may in fact add some phase to the signal itself. So we have the phase of the transverse magnetization, but when it's received by the system may add an additional phase, which we call the receiver phase. There's a lot of trigonometry, there's a lot of algebra that sort of comes in between until we finally have a high frequency voltage signal. And so this high frequency voltage signal has a lot of important sort of components to it, and it's good to be able to identify what the individual components sort of imply or infer. Not important to sort of memorize this expression. So what do we see? Well, we're of course integrating over the detectable object, everything that's been excited. We have the carrier frequency, which could be a function of space. We have the B receiver sensitivity, the coil sensitivity, which we'll see can also be a function of space. Our coils are not uniformly sensitive to all spins in the volume. We have the initial state of the transverse magnetization just immediately before we're trying to detect the magnetization, but it's of course decaying as a function of T2, it's transverse magnetization. And then there's some additional phase terms here that depend on the local Larmor frequency, which can vary because of gradients, some excitation phase, some receiver phase, and then there's some constant terms that fall out of this as well. So again, good to recognize the terms, not terribly critical to sort of memorize an expression like this. Okay, so here we have some pictures that describe sort of graphically the coil sensitivity and phase. And so we have two coils that were used for this experiment. One coil was placed towards the bottom of the object, and therefore it has a higher sensitivity for spins that are near the bottom of the object. You can see the signal is brighter here than it is at more distant aspects. And the second coil was placed on top of the object. And so the signals that are received by this coil are brighter near the coils, near the proximity of the coil, and of course fall off as you get more distant to the coil. So this describes what we generally call the coil sensitivity, or the magnitude of the coil's ability to detect the overall transverse magnetization. And of course we want highly sensitive coils because they'll boost the signal that we're receiving relative to any noise that's also acquired. The coils, however, also will impart some phase on the underlying received signal, and so you can see that each coil itself actually imparts a unique phase pattern to the underlying object. And so depending on the specifics of the imaging information that we really need to reconstruct, we may or may not care about these coil sensitivity, the coil sensitivities or the coil phases themselves. So here's a qualitative example of images obtained from 4 different individual coils. These are dynamic cardiac images. We typically place coils on the anterior aspect of the chest and the posterior aspect of the chest, and then we could reconstruct individual images from each of these coils, although more typically we would combine information from all of these coils to make a more uniform image. Okay, so let's look again more closely at this voltage signal. It is a rather complicated equation. What happens next in the MR system is that this voltage signal is multiplied by a baseband frequency that's on resonance with the Larmor frequency. We then low-pass filter it to just get back the signal that effectively is the rotating frame signal. And by multiplying by both a cosine function here and a sine function here, we get 2 different outputs, 2 voltage signals that are both phase sensitive detected. And the combination of these signals is what actually results in a signal that's a function of time, because we were recording information over time. And this signal is kind of interesting because it contains, it's how the transverse magnetization becomes detected as a complex signal through so-called phase-sensitive detection. We get phase information as well as the magnitude information. And it on information in the rotating frame as well, because we've demodulated through low-pass filtering the baseband frequency on resonance with the Larmor frequency, for example. So, again, a fair bit of math to sort of get to this point, but what we end up having then is a time-dependent signal, S, and it's an integral over the object again, so we're picking up all of the signal that was excited in the object that was within the receive field of the coil. And so this integral represents Faraday's law of induction. We again see that the coil sensitivity is still here. It's the complex conjugate of the coil sensitivity. That's not terribly important right now. We, of course, want good receiver systems, so we typically want this component here to be high, and we pay a lot of money to have high-performance coils so that we receive as much signal as possible. This transverse magnetization, of course, contains the image contrast information that we've arrived at after a series of, say, RF pulses. And that's at the time we begin our image acquisition or signal reception. And of course, that signal is going to decay a little bit with time, and that term is dropped out at this point, just to focus more on the spatial frequency encoding term, which is the last term shown here. Okay. So let's continue to think about this a little bit more. We have the spatial frequency encoding term that showed up here, and it's related to the range of frequencies that are imparted within the spin system as a function of the applied gradient. And you'll have a range of frequencies, of course, because you'll have a range of positions that were also excited. And so it's really by substitution that we introduce this definition of k-space, or a k-vector, that relates to the specific spatial frequencies, if you will, that are being received at any particular point in time. More generally, we can write down a definition of the k-space vector, which is gamma by 2 pi, and it's just the time integral of the gradient waveform. And so this is where we begin to see a tight connection, of course, between k-space and the applied gradient waveforms during signal reception. And importantly, so let's take a look at this k-space expression and relate it more directly to the applied gradient waveforms. So if we think, for example, of a rect function gradient, so we're just turning the gradient on for some period of a finite period of time, and then we're turning the gradient off. At the beginning, before we've actually turned the gradient on, we can estimate the k-space function at this point. This will just be 0, and so we're just at the middle of k-space at time 0. As the gradient is turned on for longer periods of time at a constant amplitude, we're simply moving out sort of further and further and further in k-space. And so if we evaluate the integral for the k-space function shown above, then we'll see that we're just linearly increasing area, and we're linearly moving out further and further into k-space. And as the k-space amplitude is increasing, we're getting out to higher and higher spatial frequencies, encoding higher and higher spatial frequency information of the underlying object. So let's look at this in the context of an actual pulse sequence. Here, the spoiled gradient echo sequence. So the spoiled gradient echo sequence begins with a combination of RF excitation and a slice select gradient, something we discussed in the previous lectures. And then we play, for example, a phase encoding gradient and a frequency encoding pre-winder gradient. And we'll talk a little bit more about these in the next lecture. But the combination of these two gradients, according to the k-space equation that we showed earlier, will move us out, say, diagonally to a point in k-space, dependent on the areas of these two gradient waveforms. And the next thing that would happen after this would be readout. And the readout gradient would move us along the frequency encoding direction sort of unilaterally, one directionally. And at that point in time, we would be sweeping across k-space, opening up our ADC to receive the underlying echo signal. And we would move through this sort of trajectory in k-space. The spoiled gradient echo signal will destroy the transverse magnetization at the end of acquisition, and that inherently moves you back to the origin again in k-space. And each echo, of course, fills a line of k-space. The amplitude of the echo for the gradient echo sequence is sort of shown here, something that'll be developed later. And this is essentially just the magnitude of the transverse magnetization at the time of acquisition. So let's look at some other points, other echoes that we could acquire. We could decrease the amplitude of our phase encoding gradient, but keep our frequency encoding pre-phasing gradient the same. And we would move out to a different point in k-space, moving just as far to the left in the frequency encode or readout axis, but moving half as high along the phase encoding direction. And now we move left to right with the same readout gradient, and consequently acquire another line of k-space or another echo. And we basically repeat this process as many times as needed. So in this case, we have 5 phase encoding steps. Each time repeating an identical frequency encoding gradient allows us to sweep from left to right and acquire these 5 different echoes as shown. Finally, if we've acquired all of these echoes, then we may be able to reconstruct an image that looks like this. This is a dynamic image, so we have to get a series of these k-space samples to get dynamic images. And as this is a gradient echo image, we're actually throwing away magnetization at the end of each echo. And we'll talk about steady state sequences later in the course. And I think of steady state sequences as being friendly because they recycle the magnetization. Okay, so just one last point I want to touch on here, which is scan time. And scan time is related to the TR, the length of time from excitation to excitation, so the excitation interval. And the total scan time depends on the TR, but also the number of phase encodes. How many times do we have to acquire the phase encode lines to fill, say, all of k-space for the expected image that we want? And then perhaps the number of averages. We might repeat the entire acquisition multiple times to improve the overall signal to noise. And so this is a very simple expression that gives us some insight about total scan times. We typically get 1 phase encode step per TR, and each phase encode step typically acquires 1 echo. So for example, we want to acquire about 128 echoes, or NKY, which is the number of phase encodes per image. That's a typical value for just a nominal image resolution. Then we could see that the total scan time here could easily be many minutes. So our TR might be 2,500 milliseconds, and then just multiplying by the number of KY lines, we'd come out to see that this would be a 5-minute acquisition. Now, there's a huge range in possible TRs, but the TR is oftentimes dictated by the kind of image contrast that we want to acquire. And so we don't always have complete flexibility in how we choose that. So the point is that with very simple or straightforward acquisition techniques, image acquisition times can actually be quite long, and this class will in part explore ways that we can acquire imaging data even faster. So one of the questions you might be asking at this point is, how do the gradients and k-space actually help us encode images? We didn't really talk about frequency encoding and phase encoding very much, except for at the very end. And for that, you can turn to the next lecture. Thanks again for joining us in Rad229, and click below for the follow-up lectures.